The simplest circuit we'll consider consists of a voltage source. You can just think of a battery with the positive terminal here and the negative terminal here. A capacitor, which is simply a device that has two locations from which you can draw charge or onto which you can deposit charge. A resistor is simply something that resists the flow of current, the flow of charge through the circuit. More specifically, your voltage source has the ability to repel positive charges from this end or to attract negative charges to this end. To repel negative charges from this end. Now, I haven't written it down, but the positive side would also have the ability to attract negative charges toward it, just as it repels the positive charges. The negative terminal would attract positive charges and repel negative charges. So that in this circuit, if the negative terminal repels negative charges, that would tend to move negative charges onto this part of the capacitor. And if the positive side repels positive charges, it will tend to deposit positive charges on this side of the capacitor. And you can then think of the source as pulling positive charges off of this end and pushing them onto this end, or alternatively pulling negative charges from this side and depositing them on this side. The net effect being to move charges in such a way that this side builds positive charge and this side builds negative charge. The resistor has the effect of slowing the process. Now, the capacitor, of course, has the property that having built positive charge on this side, it's going to tend to repel positive charge in this direction, which is opposite to the tendency of the voltage source to push positive charge in this direction. Similarly, the negative charge on this side of the capacitor would have the tendency to repel negative charges, which is opposite to the tendency of this side of the source to repel negative charges. So that as the capacitor builds charge, it tends to fight the effect of the voltage source, meaning that charge is going to continue to be transferred, but at a slower and slower rate. And this is going to give rise to an exponential approach to some limiting charge on the capacitor, and we'll see how that works. In a circuit involving metallic conductors, it's negative charges that get moved around. We have free electrons in the metallic components of the various circuit elements, and a voltage source with a positive here and a negative here is going to tend to pull the negative charges toward the positive end and repel negative charges from the negative end. Pulling positive charges toward this end is going to pull positive or negative charges off of this part of the capacitor, leaving that part positively charged, and it's going to tend to push negative charges around here, leaving this side negatively charged. If we have a circuit like this with an initially uncharged capacitor and a voltage source, once we close the switch, the positive side of the capacitor, being the one that's facing the positive terminal of the voltage source, is going to tend to start accumulating positive charge, and the opposite side of the capacitor, facing the negative side of the voltage source, is going to tend to accumulate negative charge, or some semblance thereof, so that we're going to build positive charge here and we're going to build negative charge here, which, as we've said, acts in opposition to the tendency of the source to push positive charge this way and negative charge this way. So once we close the switch, charge begins to accumulate on the capacitor, which slows the rate of charge transfer, and we get a charge versus time graph that looks something like this. We can look at a bigger version of this graph and see what some of the parameters are that govern this situation. Okay, here we again have the charge and the time, and we see the charge approaching some maximum charge. It approaches more and more slowly for the reasons we've talked about. Now I've drawn a dotted line here, and I've labeled this Q max. But as you see, that now reads Q sub EQ, standing for equilibrium. So Q sub EQ is Q equilibrium, and what that is the capacitor charge at which the capacitor and the source are in equilibrium. If the capacitor develops enough charge, then its tendency to push positive charge this way will be equal to the tendency of the voltage source to push positive charge in this direction. So having developed that charge, we call that the equilibrium charge. We also define C, which we call the capacitance, to be the ratio of that equilibrium charge to the source voltage. More generally, the capacitance is just the ratio of charge to voltage, where the charge is the charge on the capacitor, the voltage is the voltage of the capacitor. And there are a couple little details that I haven't explained there, but this is not too difficult to understand. Now in this picture, the time scale of the picture, which hasn't been labeled, depends on the resistance. And of course on the way the curve is drawn. But once the curve is drawn, we can then impose a time scale that fits whatever the resistance happens to be. Now again, glossing over a few details, but this is intuitively not too difficult to understand. The rate at which the charge on the capacitor changes is going to be equal to some constant times the voltage of the source. The voltage of the source is how strongly the source tends to move positive charge around the circuit. And the proportionality, the rate at which the charge changes, will be the difference between the voltage of the source and the voltage of the capacitor. The voltage of the capacitor being the tendency of the capacitor to push back this way. Now generalizing this relationship, which could easily be written as voltage of the source equals charge at equilibrium divided by the capacitance, whatever the charge on the capacitor is, the voltage of the capacitor is going to be the ratio of charge over capacitance. Okay, this is consistent with what we wrote here, and it's just a generalization, and we're not going to get that deep into the physics to see why we have these linear or inverse proportionality, direct or inverse proportionalities and so forth. Okay, we're just going to accept that much. The point is, it's the difference between the push of the source and the push of the capacitor in the opposite direction that determines the rate at which charge is going to accumulate on the capacitor. And this is a simple differential equation, which we easily solve by separation of variables. We'll divide by this factor in parentheses, we'll multiply through by dt, and we can do the integral, and you can verify very easily that if we take the derivative of this term, we do end up with reciprocal of Vs minus Q over C. And this is a familiar type of solution. We end up with Vs minus Q over C equal to some constant times e to the negative k over c times t. Of course, dividing by the c here and the negative c. once more, we assume that we understand these details at this point of the course. And we end up then with the solution Q, Q of course being a function of T, being voltage of the source times the capacitance minus this term, where I've now invoked the fact that this thing we call resistance is going to be inversely proportional to this constant here. This constant is what we multiply by the difference of the two voltages to get the rate at which charge changes. When there's a high resistance, this rate of change is going to slow because charge will pass through the resistor more slowly if the resistance is high. So that if charge passes more slowly, that means that K is going to have to be smaller. So that this thing we call resistance and K are going to be in a reciprocal relationship. So we're just going to define resistance to be the reciprocal of this constant that we wrote here. And in that case, we get this solution. Now from here we see that the voltage of the source is the equilibrium charge divided by the capacitance. The equilibrium charge is the voltage of the source multiplied by the capacitance, so that this term becomes the equilibrium charge. And then if we apply the fact that Q of 0 equals 0, which is the case if we've thrown the switch at the t equals 0 instant, we conclude that A also has to equal Q, the equilibrium charge, Q sub EQ. So that Q of t is the equilibrium charge times 1 minus e to the negative t over RC. And this models an exponential approach of the charge to the equilibrium value.